Hi, I'm Rudini Sampaio from Federal University of Ceará in Fortaleza, Brazil. I will talk about graph convexity partisan games. This is a joint work with Samuel Araújo, João Marcos Brito, also from Fortaleza, Brazil, and Raquel Folz and Rosiane Freitas from Manaus, Amazonas, Brazil. So I will talk about graph convexity games. In 81, Harari and Nieminen introduced the first paper on general graph convexity in English. In just 3 years later, Frank Harari introduced the first graph convexity games. In these games, we have a set L of labeled vertices, and the interval of the labeled vertices is the set L and any vertex in a shortest path between two vertices of L. For example, if we have these two vertices here in the set of labeled vertices, then these two vertices and also the initial vertices are in the interval of L. Okay? So the closed interval game, we have two players, Alice and Bob, that label unlabeled vertices of a graph that are not in the interval of the labeled vertices. This is an impartial game. There is no forbidden unlabeled vertex for a player. In the normal variant, the last to play wins. In the misère variant, the last to play loses. For example, let's play this game here in this graph, in this tree. Suppose that Alice is the first to play. Alice is always the first to play, and she plays this vertex. Okay, if Bob plays here, then Alice can play here. Bob played here, and this vertex is now forbidden. Alice played here, and now this vertex is forbidden. So if Bob plays here, Alice plays here, and she wins the normal variant, okay? If Bob plays here, then Alice plays here, being the last to play, winning the game, okay? If Alice plays here again, and Bob doesn't play here, but play here, for example, then Alice plays here, and these vertices are now forbidden. If Bob plays here, Alice plays here, winning the game. If Bob plays here, Alice can play here, winning the game. Another example, if Alice plays here and Bob now plays here, so Alice plays here. For example, plays here. If Bob plays here, Alice plays here. Bob and Alice is the last to play. Alice wins. If Bob plays here, Alice plays here. This vertex is forbidden. This is forbidden. Alice is the last to play. So Alice can win the game. So that is, Alice has a winning strategy here. So the decision problem of this game, the closed interval game, is to decide which player has a winning strategy. Okay, so this game is very associated with the NIM game. In the NIM game, players remove objects from heaps. For example, we have here 3 heaps, this one with 3 objects, this with 2 objects, and this with 1 object. The last to play wins. A player selects 1 heap and remove any number of objects from that heap. Bouton solved the NIM game in the beginning of the last century, and this game is very important in the Sprague-Grundy theory from the 1930s that relates every impartial game to a NIM game. Okay? So in this case of this example of the tree, if Alice is the first to play, Alice is always the first to play, sorry, and she plays here, we have the same situation of this NIM configuration. We have 3 objects here, 3 vertices here, 2 objects here, 2 vertices here, and 1 object here, 1 vertex here. Okay? So with this, It was proved in the theoretical computer science in the last year that this impartial closed interval game is polynomial time solvable in trees. In this game, in this paper of COCOON, we extend these results to the Partizan variants of convexity games. Let's begin with the Partizan interval game. We proved that it's polynomial time solvable in trees. In a Partizan game, the vertices, the elements, have owners. Only the owner can label, can select the vertex. Okay? We prove that the Partizan closed interval game is polynomial time solvable in trees. Here we have an example of a configuration of the Partizan closed interval game. We have just one vertex labeled at the beginning, in this example, and this vertex, the owner is Bob. This vertex with B, Bob is the owner, and this vertex with A, Alice is the owner, okay? So, for example, if Alice is the first to play, if she plays here first, these vertices are now forbidden because of this shortest path here. Then Bob can play here, Alice can play here, and this vertex is forbidden. And Bob can play here, Alice plays here, and then Bob plays here. Bob is the last to play. Okay, Alice started and Bob wins. If Bob is the first to play in this example, for example, Bob can play here. Alice can play here, and these vertices are forbidden. And then Bob can play here, Alice can play here, and then this vertex is forbidden. And Bob plays here, and Alice plays here. Alice wins the game, the normal variant. Bob started, and Alice, if Bob starts, Alice wins, okay? This is what we call a zero game, a position with value 0. The first to play loses the game, okay? So there is a very nice theory, combinatorial game theory, in the book Winning Ways for Your Mathematical Play from Berlekamp, John Conway, and Richard Guy from 1982 that associates every position of a Partizan game with a number. One of the most important games of this book is the red-blue Hackenbush game. In this game, we have lines, and the players cut lines, okay? So this position here of our game, Partizan closed interval game, is directly associated with this position of the red and blue Hackenbush game. For example, if Alice can only cut the blue edges, the blue lines, and Bob can only cut the red lines. If Alice is the first to play, Alice plays here, Bob plays here, Alice plays here, Bob plays here, Alice plays here, and then Bob plays here. Alice started, and Bob wins. If Bob starts here, Bob can cut this, Alice cut this, Bob cut this, or this, for example. Alice cut this, Bob cut this, and then Alice cut this. Bob started, and Alice wins. This is a game with value 0. The first to play wins, okay? Using this very nice theory, it's not a direct association. We have graphs with that is not directly associated with Hackenbush positions, but we could use this theory to prove that Partizan closed interval game is polynomial time solvable in trees. Okay, we also obtained computational complexity results. We proved that the How games, that is also a convexity game, are p-space hard. So in the closed How game, Alice and Bob label unlabeled vertices of a graph that are not in the convex hull of the labeled vertices. The convex hull is obtained after successive applications of the interval function on the labeled vertices. For example, if we have two vertices here in the graph H that are non-adjacent, for example, and they are labeled, this vertex is in the interval because of this shortest path. This vertex is in the interval of these vertices because of this path, also this, and also this. Okay? And again, since this vertex is in the interval of these two, and this vertex is also in the interval of these two, if we take the shortest path between these two vertices, all vertices of the graph H are in a shortest path from them. Then that is the convex hull of two non-adjacent vertices of H takes all vertices of the graph. Okay, the convex hull of just two vertices, non-adjacent vertices of H is the entire graph. Okay. Okay, so this gives us a very good idea of the main idea of the proof. The reduction is from the partisan clique forming game. In this partisan clique forming game, we have a graph H, and the vertices are have owners. From some vertices are from Alice, other vertices are from Bob. Alice can only select vertices, her vertices, and Bob can only select his vertices, okay? And we show that if in the Misère variant of the convex in the closed hull game, we saw that we cannot select two non-adjacent vertices of H or in the G prime graph, in the entire graph. The reduction is from this clique forming game, partisan clique forming game. So because if we take two non-adjacent vertices, all the graph is taken, the game ends, and the last to play loses the Misère variant. Okay, this is the main idea of the proof for the Misère variant. It's the easiest one. But in the normal variant, we have a more complicated case, and I will not explain. But again, we use the partisan clique forming game, but the normal variant of the partisan clique forming game that is also p-space hard. The normal variant was proved in 1978 too. And here we also have owners. Each verse has owners. For example, here, these verses are from Alice. Only Alice can label these vertices. Here, these verses are, the owner is Bob. Only Bob can select these vertices. Okay? So we also prove that the normal variant of the partisan closed hull game is p-space hard, p-space complete. Okay. We also obtained other results from other graph convexity games. Paul Erdős in 1972 obtained results in geodesic convexity in tournaments that are complete directed graphs. The geodesic convexity, as we saw, was introduced by Frank Harry and Nieminen in 1981 in undirected graphs. The monophonic convexity is related to induced paths instead of shortest paths in undirected graphs. Regarding directed graphs, we can relate any red-blue Hackenbush position to a closed interval game. This example here is the direct association with this configuration of red and blue Hackenbush. For example, this line blue is related to this blue vertex, this blue and red, red, blue and blue, red, blue and blue vertices here. These lines, blue and red lines here, blue and red vertices. Okay, so we obtain very nice results here relating these two games, and also we obtain results from convex geometries regarding other games but I don't have time to explain all of them. Okay, that is, thank you very much. Here are these three guys here are from Fortaleza, Brazil, and these two girls here are from Manaus, Amazonas, Brazil. Here are me, Rudini, João Marcos Brito, Samuel Araújo, Raquel Folz, and Rosiane Freitas. That is, thank you very much.